Hello, I'm Robert Miles. Welcome to this recording of the Alignment Newsletter podcast. This is newsletter number 124, Provably Safe Exploration Through Shielding, published on the 4th of November 2020 by Rohin Shah. Highlights. Link, Neurosymbolic Reinforcement Learning with Formally Verified Exploration by Greg Anderson et al., summarized by Rohin. A typical approach to formally verified state exploration in RL is to compute a shield which identifies a safe set of states and actions. After this shield is computed, it's wrapped around the environment to ensure that if a potentially unsafe action is about to be taken, it's replaced with a safe one. Then, a policy learning algorithm is applied as normal to learn a good policy. The key insight of this paper is to compute shields for specific policies, rather than creating a one-time shield that must apply to the entire state space. Since any given policy will only visit a small fraction of state space, the shields are easier to compute and can be more permissive. They assume access to a worst-case dynamics model, which, given a state and action, outputs a set of states that could be visited. Given a policy pi, an inductive safety invariant is a set of safe states that includes all possible initial states and is closed under worst-case transitions. If you start at a state in the set, for any action that pi suggests and for any state from the worst-case transition dynamics, that new state will still be in the set. Our algorithm will ensure that any policy we execute will have a corresponding inductive safety invariant. Formal verification techniques allow us to find inductive safety invariants for restricted classes of policies. This paper uses the space of deterministic piecewise linear policies as its set of symbolic policies. But how do we apply this to neural nets? The key idea is to start with a safe symbolic policy, convert it to a neurosymbolic policy, take a neural net gradient step, convert back to a safe symbolic policy, and repeat until done. Let's go over each of these steps. First, let's suppose we have a symbolic policy G with inductive safety invariant O. It's actually represented with the empty set symbol, but I'm calling it O to make it easier to pronounce. Then, for any neural net F, we construct a policy H, which is f of s if no matter what we stay within O, otherwise g of s. It's easy to see that O is also an inductive safety invariant for H. Which f should we use to create H? The authors train a neural net to imitate G and use that as their f. Note that imitating G only requires executing G in the environment, and we know that G is safe. Now that we have our neurosymbolic policy H, we need to take gradient steps on it. We collect data in the environment using H, but then, for the gradient, we ignore the symbolic part and take a gradient step as though the data were collected using F. It seems that they used an on-policy algorithm for this, introducing bias. I'm not sure why they didn't simply use an off-policy algorithm. This produces a new neurosymbolic policy, H', that is still safe, since G and O are unchanged and that's what guarantees safety. Finally, we need to convert H' back into a symbolic policy G'. This is done by a version of imitation learning that works in the symbolic policy space, where a new inductive safety invariant for G' is found using formal verification techniques. To start off the whole process, we need an initial symbolic policy, which must be constructed by hand. The authors show using experiments in simple continuous control environments that this method can learn high-reward policies without ever having a safety violation. Rohin's opinion. I really like this as an example of combining the performance of neural networks with the robustness of symbolic approaches. I especially like the fact that the shield is specialized to the current policy and updated over time. I think ML scales so well partly because it only deals with a tiny portion of the input space and can completely ignore the vast majority of possible inputs. And so if you want to add anything on top of ML, you need to ensure you preserve this property to ensure scalability. Previous approaches required a shield that's correct across all possible states, failing to preserve this property. In contrast, this approach only requires a shield that's correct for the sequence of learned policies, on whichever states they visit. I should note that a large portion of why I like this paper is that it feels like it elegantly fits in both the formal verification and the ML fields. I used to work in programming languages, of which formal verification is a subfield. On the formal verification side, the guarantees are clean and simple, and the techniques used are canonical. On the ML side, I mentioned above why I like the fact that the shield is policy-specific and updated over time. As I've said before, I think the real challenge in formal verification for AI alignment is how to handle fuzzy specifications. I think this paper shows a path forward. Since the safety is established by an inductive invariant that can change over time, we could potentially use human feedback to establish these inductive invariants and update them over time without requiring a human to fully specify at the outset exactly what is safe and what isn't. You could think of it as an expanding whitelist of states which the policy is allowed to visit. Section Technical AI Alignment. Subsection Learning Human Intent. Link Imitation Learning in the Low Data Regime by Robert Dadashi et al., summarized by Zach. Non-adversarial imitation learning, from newsletter 119, has become more popular recently due to the fact that GAN-style architectures can be notoriously unstable during training. This paper makes a contribution by introducing an imitation learning strategy that relies on minimizing an upper bound on the Wasserstein distance between the imitator and expert state visitation distributions. The Wasserstein distance can be understood using the earth movers analogy. In this interpretation, we view the distance as the cost of the most efficient transport strategy to move probability mass from the imitator distribution to the expert distribution. The advantage of such an approach is that the metric can be calculated in an offline way. If we calculate the distance for partial rollouts, then we can create a dense, albeit non-stationary, reward for the imitator. In experiments, agents trained using the Wasserstein distance are able to learn control tasks using only a single trajectory. If you want to read more, you can read the paper Primal Wasserstein Imitation Learning. Zach's opinion. With this paper, I conclude that IRL works for Mujoko-style control tasks. The performance of this method is similar to offline Gale, but is better justified and more stable. However, ultimately, I'm a bit skeptical of their claim that the method will generalize to other tasks. Results for Gale/DAC are quite poor in Atari-like environments, whereas pairwise reward modeling seems to perform quite well. This would suggest a reward modeling approach would scale much better in more complicated settings. Subsection Verification. Link An Inductive Synthesis Framework for Verifiable Reinforcement Learning by He Zhu et al., summarized by Rohin. This older paper has a pretty similar idea to the one in the highlighted paper. In order to compute a safety shield for a neural network RL agent, we first transform the neural network into a simpler, more symbolic policy, prove safety of the symbolic policy, and then use the generated inductive safety invariant as a shield. This paper also uses deterministic piecewise linear policies as its space of symbolic policies. It only proves safety of the final learned RL policy, and so only guarantees safety at deployment, not at training time. In other words, it does not guarantee safe exploration, and instead assumes that you're training in simulation so that safety is not a concern. Rohin's opinion. Since this paper was published at PLDI, it's both longer and goes into a lot more of the details of how to actually perform each of these steps, as well as showing it with a running example on the inverted pendulum, where safety is defined as not going beyond a certain angle. I'm not going to summarize them here, but anyone interested in these technical details should check out this paper before the highlighted one, which is constrained by ML page limits and can't explain the techniques very well. Just as a reminder that learning programs does not automatically confer interpretability, I present to you the symbolic policy learned by their method for the inverted pendulum. There follows an image of a program which, although it's only maybe 7 lines long, each of the lines is a sequence of terms multiplied by constants and raised to powers. It starts, if 17,533 n to the 4 plus 13,732 n to the 3 omega plus 3,831 n squared omega squared minus 5,472 n omega cubed, and so on for another 6 or 7 terms, and then it's checking if that is less than or equal to 0 before it returns minus 17.28176.866 n minus 10 point. You get the idea. This program is not human interpretable. Link Verifiably Safe Exploration for End-to-End Reinforcement Learning by Nathan Hunt et al., summarized by Rohin. As we saw in the highlight, applications of formal verification to reinforcement learning and safe exploration often rely on shielding, in which any proposed unsafe actions are replaced by randomly chosen safe actions. Typically, this requires having an MDP model in a high-level symbolic state space, such as by defining the MDP over the Atari simulator space, rather than learning from pixels. This paper demonstrates that we can relax this requirement and learn policies on low-level observations, while still getting the safety guarantees of the shielding approach. The approach is simple. We define, manually, an abstract model of the environment, with a symbolic state space and dynamics model, and use this to create a shield as usual. Then, to learn the policy, which gets pixels as input, we use an object detector to transform the pixels into a symbolic state, and then use the shield if necessary to select which action to take. The authors show that as long as the error of the object detection step is low, the overall policy learning will remain safe. Link: Enabling certification of verification-agnostic networks via memory-efficient semi-definite programming by Sumanth Dathatri, Krishnamurthy Dvijotham, Alexei Kurakin, Aditi Ruganathan, Jonathan Uesato et al. Summarized by Rohin. In parallel with extending verification to sequential settings, as well as learning what specifications to verify, we also need to make verification significantly cheaper in order for it to be feasible to apply it to large neural networks. So far, we've only been able to achieve one of two very desirable properties at a time. One, the method can scale up to large, independently trained networks. This has been achieved by methods using linear LP relaxations, like the one in Newsletter 19. Two, the method produces tight bounds and thus avoids producing vacuous results, achieved by using relaxations based on semi-definite programming, SDP, instead of linear ones. This paper shows how you can massage the SDP version such that the resulting algorithm becomes scalable, changing the runtime and memory requirements from O of n to the 6 and O of n to the 4 to O of n per iteration. The resulting algorithm can be applied to larger neural nets than previous SDP approaches and gives much tighter bounds than LP approaches. For example, on an adversarially trained CNN for MNIST, which SDP algorithms haven't previously been applied to, they can verify 87.8% adversarial accuracy, while LP methods can only verify 0.4%. Section Other Progress in AI. Subsection Reinforcement Learning. Link: Fast Reinforcement Learning Through the Composition of Behaviors by Andre Barreto et al., summarized by Flo. While model-based RL agents can easily adapt their policy to changed rewards on the same environment, planning is expensive and learning good models can be challenging for many tasks. On the other hand, it's challenging to get model-free agents to adapt their policy to a new reward without extensive retraining. An intermediate solution is to use so-called successor features. Instead of a value function, v of pi and s, representing the expected discounted rewards for a policy pi starting in a state s, successor features are a vector-valued function psi of pi and s, representing an expected discounted feature vector phi. If our reward r equals w multiplied by phi for some weight vector w, we can easily obtain the original value function by taking the scalar product of the successor features and the weight vector. V of pi and s equals w multiplied by psi of pi and s. Successor features thus allow us to evaluate a fixed policy pi for all rewards that are linear in phi, which is called a generalized policy evaluation. Now that we can evaluate policies for different preferences, we would like to efficiently find a good policy for a given novel preference. Inspired by human learning that often combines previously learned skills, we deploy generalized policy improvement. In vanilla policy improvement, we improve upon a policy pi we can evaluate by choosing the action that maximizes the value v of pi and s prime of following pi starting in the next state s prime. In generalized policy improvement, we have multiple policies and choose the action that maximizes the max pi of v of pi and s prime, the value of following the best of these policies starting at the next state s prime. To obtain a policy for the new preference, we stitch together all policies we learned for previous preferences, and the resulting policy performs at least as well as all of the old policies with respect to the new preference. As generalized policy improvement does not require any additional environment samples, it enables zero-shot transfer to new preferences. Empirically, even if the weight vector w has to be learnt from reward signals, generalized policy improvement is very sample efficient. Additional examples can then be used to further improve the policy using standard RL. Flo's opinion. I really like the idea of successor features. Similar to model-based systems, they allow us to evaluate policies for many different rewards, which can be used for anticipating problematic behavior before deploying a system. However, note that we still need to execute the policy we obtained by generalized policy improvement to evaluate it for different rewards. The only guarantees we have is that it's better than the previous policies for the reward for which the improvement step was carried out, and potentially some weaker bounds based on the similarity of different rewards. Link: Does on-policy data collection fix errors in off-policy reinforcement learning? By Aviral Kumar et al., summarized by Flo. Q-learning finds the optimal Q function Q star by updating our estimate Q of S and A for a state action pair S and A to get closer to the immediate reward plus the discounted Q value for the best action A prime in the next state S prime. To generate samples, we usually pick actions corresponding to high Q values. In bandit problems, where S prime is always terminal and thus has all Q values at 0, this leads to corrective feedback. If we overestimated an action's value, we'll pick this action again soon and are quickly able to correct our misconception. In general MDPs, corrective feedback can be a lot weaker, as our update of Q of S and A also depends on the Q values for the next state. To get corrective feedback, we need somewhat correct Q values for the next state. But to get these, we likely need good values for the second to next state, etc. This is particularly problematic with function approximation, as updating the current state's Q value might lead to a worse estimate for values down the chain. Consequently, we might see convergence to suboptimal Q functions, unstable learning, or problems with sparse or noisy rewards. To deal with this, we would like to first prioritize correct estimates for states near the end of the chain. But in many branching problems, we actually observe these states with the least frequency, such that their values are influenced disproportionately by other states' values when function approximation is used. The author's approach, dubbed DISCOR, reweighs the data distribution to account for this. We would like to preferentially sample states for which we expect Q to be close to Q star after the update, and thus give more weight to state action pairs when we expect the error, the magnitude of Q star minus Q, to already be small. As we don't know Q star, we rely on a bound for the error at a state action pair S and A equal to the sum of the magnitudes of previous updates down the chain plus the initial error, discounted as we move back in time. Thus, the error in the next state one step ago is discounted by gamma, the error in the second to next state 2 steps ago is discounted by gamma squared, and the initial error is discounted by gamma to the k. This bound can be approximated by a neural network using a Sarsa-like update rule, for which the influence of the unknown initial error fades for large K due to the discounting. DISCOR is evaluated on meta-world tasks in both the single and multitask setting, and SAC augmented with DISCOR clearly outperforms SAC in many settings. Similar improvements can be observed for DQN on Atari. If you want to read more, you can read the paper DISCOR, Corrective Feedback and Reinforcement Learning via Distribution Correction. Flo's opinion. Putting less weight on updating values with fluctuating targets seems like a good idea. As the approach does not require much additional compute if weights are shared for the Q network and the network estimating the bound, and as it seems quite orthogonal to previous improvements to methods based on Q functions, I would not be surprised if it became somewhat widely used. This concludes Alignment Newsletter number 124. For more information, you can go to rohinshah.com/alignment-newsletter, where you can find all of the previous newsletters and also a spreadsheet of all of the papers and summaries that have ever been featured. Thank you for listening.